Hello and welcome to this video for CE 108 Mechanics of Deformable Solids. So we are still in chapter 1, and so in the previous videos we have seen a review of what are the different types of external forces that can be applied to a given material. Those are the forces that you know. And then based on those forces that you know, typically you will want to calculate the forces that you don't know. Those forces can be the reaction that are applied by the support and the internal forces that are taking place inside the material at each point inside the material. So now what we are going to see is if you want to calculate the internal load at a given position at a given point within these materials, for this we will need to use the method of section, and we are going to see what's the general method, what are different steps to apply this method of section to calculate the internal loads that are acting inside a material at a given point. So whatever is the body equilibrium problem that you are trying to solve, and whatever is the type of internal load that you are trying to calculate, you can always solve this problem by applying the same steps, which are going to be a general method that can be applied to any problems, any types of system, irrespectively of the types of external forces or external moment that are applied to this material. So let's review what are the different steps that you should be following. So the first step, which is always true in most mechanics problems, is to draw the free body diagram. So that's always going to be a first thing that you should be doing is you draw the free body diagram, FBD. So the point of the free body diagram is to specify what is the system that you are isolating. And sometimes it's not obvious. If you have a system that is a structure that is made of different members that are attached to each other, you need to specify what are you isolating. When I say what isolating, I mean that you need to define what is the system that you are considering, and everything behind inside the system will be considered as internal. For example, the internal forces will be the forces that are inside the system, and everything that is outside the system will be the exterior, and so they will be contributing external forces. So you need to draw the free body diagram. The free body diagram consists in thinking that first you isolate a given system, a given body. You assume that this body is initially free, so that's why it's called the free body diagram. It's initially free to move, and then you identify all the external forces that are applied to this body that prevents this body from being free. So the step one is always going to be to draw the free body diagram and to identify the external forces. So you identify what are the external forces that are applied to the system that you are isolating. And again, we need to be careful here that whether a force is internal or external, that depends on the system that you are isolating. So that's why you need to draw the free body diagram. You need to specify what is the system that you are isolating. And then based on what you are isolating, everything that is outside the system that you are isolating becomes an external action. Those are what can potentially apply some external forces or some external moments to the system that you are isolating. So that's step one. Free body diagram, identify the external forces. Then once you have drawn your free body diagram, now you will identify the unknown forces. So you will identify the unknown reaction from the support. Identify and draw the unknown forces, the unknown reactions from the supports. So the unknown reaction from the support. So it's important to identify them, which means that you need to look what are to which types of support is your system attached. Again, this depends on what is the system that you are isolating. You need to look at what is the system that you are isolating, what are the supports it is attached to, pin, roller, or fixed support. And then you need to look for each support, how many unknown reaction forces does it create. 1 for the roller, 2 for the pin, 3 for the fixed support. And then you need to draw them. It's important that you draw them, because when you draw them, you draw them in one direction. For example, you draw a force going up, going down, going towards the left, or going towards the right. And the way you draw it will define the sign of this reaction. So it's important to draw it so that I can know if you are drawing this force as pointing towards the right or pointing towards the left. When you draw a reaction force, you can always draw it the way you want. You can draw it towards the left, towards the right. This doesn't matter. But you need to be consistent between what you draw and what appears when you write the condition of equilibrium. So it's important that you draw the unknown reaction so that I can know what is the convention, or what is the sign that you are using when you define those reactions. So once you have drawn the free body diagram, step 1, once you have identified and drawn the unknown reaction, step 2, then you move to step 3. Step 3 is to write the condition of equilibrium. So you will write the equation of equilibrium for the system that you are isolating. So in this case, when I say condition of equilibrium, that's what you saw in statics. The sum of the external forces along x equals 0, the sum of the external forces along y equals 0, and the sum of the external moment about a given point, O for example, is equal to 0. So this is only about the external forces, right? So you need to isolate a given system and figure out what is the external forces. So the external forces, the one that you know plus the reaction, those are the only forces that should be appearing in the equation of equilibrium, not the internal forces that we want to calculate. So this, if you do that, so if you say that the sum of the forces and of the reaction must be summing up to 0, it means that since you know what are the external forces, those are the known forces, that is going to allow you as an outcome to calculate the unknown. So this is going to allow you to calculate the unknown reaction forces. So this is step 3. At the end of step 3, you should be able to calculate the unknown reaction from the supports. Then, so we move to step 4. So far, what you have done is to calculate the unknown reaction, which is good, but our goal is to calculate the internal loads acting at a given point within the material. So for this, we need to use the method of section. So in this case, we are going to use the method of section, which means that if you want to calculate the load acting at a given point within the material, you need to define a section that split the material into 2 parts, and a section that goes through the point at which you want to calculate the internal load. So you define a section that goes through the point at which you want to calculate the load. So you define a virtual section that goes through the point at which you want to calculate the load, so the internal load. So this is about the method of section. So now it means that you are going to define a section, and you will be isolating either the left or the right. And now you will identify what are the forces that are applied to the section, the new section that you are isolating, and define what are the new unknowns, which are going to be the unknown forces apply by the left to the right, the right to the left, the top to the bottom, or the bottom to the top. So those are going to be the new unknown, and those are going to be the internal loads. The internal loads is the force applied by the left to the right, or the right to the left, or the top to the bottom, bottom to top, at the point at which you want to calculate this load. So you use the method of section, you define a section that goes through the point at which you want to calculate the load, and then you isolate either one or the other of the part of the materials after you have cut it along this section. And once you have used this, then you move to step 5, which is that now you will isolate one region on one side or the other of the section, and you will write the new equation of equilibrium for the isolated subsection, for the isolated subsection of the member. So you isolate either the left or the right part of the member on one side or the other of the section that you have defined that goes through the point at which you want to calculate the load, and you write the new condition of equilibrium. And at this point, this will allow you to calculate the internal load. So it's important to follow those steps. You need to first apply the condition of equilibrium for the entire member so that you can calculate the reaction support, the unknown reaction support. And then once you have done this, you can use the method of section to calculate the internal loads that are acting within the materials. So now what we are going to see is to take an example and to see how we can apply those different steps 1, 2, 3, 4, 5 to calculate the internal load within a given member subjected to some external forces. So let's consider a given system as an application. So let's consider a member like this, and so this member goes between x equals 0 to x equals 4L. So the length of the member is 4L. And so at x equals 0, this member is attached to a pin. That's going to be the point A. At x equals 4L, this member is attached to a roller. That's going to be the point B. And then in the middle, at x equals 2L, there is a concentrated force that is applied going down, so an external force applied in the middle, and so that's going to be the point D, for example. So then the question in this case, just as an example, is what if you want to calculate the internal load acting within the material at x equal L. So if you define this point C here at x equal L, you want to calculate the internal load at x at the point C at x equal L. So that's the goal of this problem here. So for this, we are going to follow the different steps of the method that we just saw, right? So we start step 1, free body diagram, and we identify the external forces. So in this case, we isolate the entire member here, and the only external forces that we know already is the force F that is going downwards, that is applied in the middle at x equal to L. Then we isolate the unknown forces. So we identify the reaction, and we step 2, we identify the unknown. So we identify what are the unknown reaction forces applied by each of the supports. So this is where you need to look at what are the supports to which the system that you have isolating is attached to, and you need to draw those supports so that you can define whether those unknown forces are going to be defined as pointing upwards, downwards, towards the left, towards the right. So in this case here, the member is attached to two supports, one pin and one roller on the right. So for the pin on the left, the pin is going to create two unknown forces that prevents the member from going up or down, and also prevent the member from going left to right, but it doesn't prevent the rotation of the member. So there are two unknown forces, one normal force NA that prevents the member from going up or down, and also a horizontal force VA. Those are the two unknown forces. At the point B, you have the roller. The roller only prevents the member from going up or down. So there's only a normal force at the point B. Those are the three unknowns that you have, right? So remember, keep in mind that here, the goal of this thing here is to calculate the internal load at the point C. So the internal load is can only be defined inside the material. So in this case, it's at the point C. And so we want the internal loads at the point C. Okay, so step 2. So we have identified the unknown. So step 3, we are going to write now the condition of equilibrium. So we isolate the entire member here, and we are going to say that the sum of the external forces applied to this member is 0. So first, sum of the forces along x equals 0. We need to look at all the external forces and take their projection along the x-axis and say that the sum of the projection of the force is equal to 0. So in this case, there is only one force that has a non-zero projection on the x-axis. So NA, VA, and F, they are all along the y-axis. Those are all vertical force, so they would have a 0 projection along the x-axis. The only force that has a non-zero projection along the x-axis is VA. So here, that's why it's important to that you define and that you draw the unknown forces. Here, for some reason, I decided to draw VA as pointing towards the left. So this, I am free to define the unknown the way I want. I can define VA as pointing towards the right or pointing towards the left. In some cases, we have some intuition about how should the reaction be. For example, here, since you apply a force F going downwards, it's very likely that the reaction of the supports will be going upwards to counterbalance the force F. So that's why I drew NA and NB as pointing upwards, because I had some intuition that if you have an external forces going downwards, you need some reaction support that are going to go upwards to counterbalance the external forces. But for VA, we don't have, there is no reason that VA should be going towards the left or towards the right. So you can just draw it the way you want. But then when you calculate the projection of VA, you need to be consistent with the way you wrote it. Here you drew VA as pointing towards the left, which means that now when you calculate when you write the projection, the sum of the projection of the forces along the x-axis, VA is pointing towards the right, pointing towards the left, sorry, but the axis x is pointing towards the right, which means that now when we write the fact that the sum of the projection of the forces along the x-axis equals 0, VA has a negative projection because it's not pointing in the same direction as the x-axis. So when you calculate the sum of the projection of the forces along the x-axis, VA is pointing towards the negative x, so its projection is minus VA. So when you write the condition of equilibrium here, sum of the forces equals 0, so it means that minus VA, which is the projection of VA along the x-axis, is equal to 0. So in this case, it means that simply VA equals 0. So there is no horizontal force that is created by the support here. Second thing, so sum of the projection of the forces along the y-axis equals 0. So now we need to project all the vertical force to the y-axis. We have two forces that are pointing upwards towards the positive y. So they will have a positive projection. So NA and NB, they will both have a positive projection because they are pointing towards the positive y. And then we have F, but F is pointing downwards towards the negative y, so it has a negative projection. And the sum of those forces is equal to 0, which means that in this case, the force F is equal to NA plus NB. So the force F has to be balanced by the sum of NA and NB, the two normal reactions of the support. So here we have so far three unknowns, NA, NB, VA, and we have only two equations. So we are not able to solve the problem just yet. So we need a third equation to calculate the three unknowns, and this third equation is going to come from the moments. So now we can write the fact that the sum of the moment about a given point is equal to 0. So here you can choose the point that you are going to choose. Like you can pick any point to calculate the sum of the moment about this point, but you need to be sure you are consistent between your calculation and the point that you are choosing. So in this case, it's always useful to calculate the moment about a point through which you have the most line of action going through. For example, here, I could calculate the sum of the moment about point A, about point C, about point D, about point B. Like all of those options would be fine, and you would be able to find the final result, whatever is the choice of the point that you are considering. But here, since we have two forces that have a line of action going through the point A, it's better to use the point A, because we know directly that a force that has a line of action that is going through a given point will create a zero moment about this point. If the point is directly on the line of action, then the arm of the force is going to be 0. And then, so that's going to simplify the calculation. So now we are going to say that the sum of the force of the moment about the point A is equal to 0. So if we do this, so now we need to look at all the other forces and to decide if they have a moment. What is the value of this moment? Is it a positive or a negative moment? So NA and VA do not create any moment about the point A because A is on the line of action of NA and VA, which means that the arm of the force would be 0. So we don't need to worry about the moment created by NA and VA. It's equal to 0. Then, so we have the moment created by NB. So the first thing is the sign. NB is going to make the body rotate anti-clockwise about 2A. So it's going to be a positive moment. So we can start with that. Then, so the moment, the intensity of the moment is going to be the product of the magnitude of the force. So NB times the arm of the force. So in this case, the arm of the force is the perpendicular distance between the point A and the line of action of NB. So in this case, this arm of the force is 4L. So this moment will be 4L times NB. And then the other force that has a line of action that doesn't go through the point A is the force F. In this case, the force F is going to tend to make the body rotate clockwise about the point A. So it's going to create a negative moment by convention. The intensity of the force is F, and the arm of the force is 2L. And the sum of this has to be equal to 0. So then, based on this, you can find directly that the unknown force NB is equal to F divided by 2. And on the other hand, since we also know that F is equal to NA plus NB, so this now allows us to calculate NA, which is also equal to F over 2. So here one thing to keep in mind is that sometimes when you see these types of problem, some of you would say it's a symmetric problem. So I know already that NA is going to be equal to NB because it's a prime that is symmetric, which in this case is true. This prime is symmetric with respect to x equal to L. So indeed, NA has to be equal to NB. But keep in mind that in general, you should be careful about using the symmetry, because sometimes prime that look symmetric are actually not symmetric. So if you just assume that the prime is symmetric, although it's not the case, then potentially you can make some mistake. So you never need to assume that the prime is symmetric to solve it. Like for example, here we can find that NA is equal to NB simply by writing the fact that the sum of the moment is equal to 0. So we never need to assume that the prime is symmetric. We can always find it usually by writing that the sum of the moment is equal to 0. So if you're not sure, I would recommend you just avoid saying that those prime are symmetric. You can just, you never need to assume that. You can just find, you can achieve and get to the result simply by writing the free condition of equilibrium that you have for the system that you're isolating. Okay, so we are at stage 3. So we have we have written the condition of equilibrium. So now we are going to move to step 4, which is the method of sections. So here we want to calculate the load at the point C. So we are going to define a section that goes through the point C, the point at which we want to calculate the load, the internal load. And now we need to decide to isolate either the left or the right. So in this case, it's always good to isolate the section that has the lowest amount, the least amount of external forces. Here it's better to isolate the left part because there is more force applied on the right part than on the left part. So it means that in this case, it's going to be preferential to isolate the left part. So we are going to isolate the left. Then, so now I mean that we define a new system. So we redefine what is the inside and what is the outside. We redefine what is internal and what is external. So we isolate the left. It's useful to redraw a new free body diagram where this time we only isolate a given section. We only isolate the left parts. So in this case, if we isolate the left, it means that we are only isolating the portion of the material that goes between x equals 0 to x equal L, which is where we cut the system into 2 parts. So we still have the pin at x equals 0. And we still have the fact that this pin is creating a given force NA that is equal to F over 2. So we have already calculated this unknown force before. And we also already know that VA equals 0, so we don't need to worry about it. Keep in mind that here now F and NB are not applied to the section that we are isolating. So those are not external forces anymore. They are not applied to the system that we are isolating. So we don't need to worry about the force F and the force NB. They are not applied to the system that we are isolating. So they should not be taken into account into this new free body diagram. Now, the only new force that we have is that because we have cut the system into 2 parts at the point C, now the right part of this member will act as a fixed support to the left part. The right part will prevent the motion, the translation, and the rotation of the left part because the left part is attached to the right part. So because the right part is acting as a fixed support to the left, so now we are isolating the left, the right becomes part of the exterior. It becomes a fixed support to the left. So it will create some new reaction support that we need to add. And those reaction support will be the internal load that we want to calculate in this case. So since the right is a fixed support, it will create 3 unknowns. Those are the 3 internal loads that we want to calculate. So in this case, so we are cutting the system at the point C. So the right is acting as a fixed support, so it's going to create 3 unknown forces: a normal force, a shear force, and a moment. So we can write those 3 internal load: VC, NC, and MC. And now, so we have identified the new unknowns for this section. So now the last thing that we need to do is to write the condition of equilibrium for the new section that we are isolating. So we write the condition of equilibrium for the left part that we have isolated. So again, sum of the forces along the x-axis is equal to 0. In this case, the only forces that we have is along the x-axis is NC. Sum of the projection of the forces along the y-axis is equal to 0. So what do we have? We have F over 2. F over 2 is pointing towards the positive y, so it has a positive projection. And then we have VC. VC is pointing towards the negative y, so it has a negative projection. So it's a negative VC. And those are the only 2 forces that we have along the y-axis. So we find, based on this, that F or VC, since VC is what we are looking for, VC is equal to F over 2. So we have found 2 of the internal loads. We have found the normal and the internal shear. The normal load is equal to 0. The internal shear in this case is F over 2. Now we just need to calculate the internal moment at this point. So we are going to write it by expressing the fact that the sum of the moment is equal to 0. In this case, since we cut the material at the point C, it's good to calculate the sum of the moment at the point C at which we are cutting the system. So we write that the sum of the moment about the point C is equal to 0. So what do we have? First, we have the moment MC that is applied by the right to the left. So this moment here. So in this case, now we need to write the sum of the projection. MC is an anti-clockwise moment, so it has a positive projection, so it's plus MC. VC and NC, their line of action is going through the point C. So those NC and VC forces will have a 0 moment about the point C because this point C is on the line of action of those 2 forces. So we don't need to worry about them. And that's why it's always good to calculate the moment about the point at which you are cutting the materials, because it means that necessarily this point will be on the line of action of the 2 vertical and horizontal unknown forces at this point at which you are cutting the material. So then the only remaining moment that we have is the moment created by the force F over 2 at x equals 0. So these forces, we need to first look at the sign of the moment. So this force is going to tend to make the body rotate clockwise about the point C. So it's going to be a negative moment. The intensity of the force is F over 2. The arm of the force is L. So this is equal to 0. So in this case, we find that the moment MC is equal to FL over 2. And so based on this, by now applying those different steps, step 1, 2, 3, 4, 5, we have now calculated the internal loads at the point C. So we have calculated the internal actual load NC, it's equal to 0. We have calculated the internal shear VC, it's equal to F over 2. And we have calculated the internal moment MC, which is equal to FL over 2. So if you want to solve a problem where you need to calculate the internal load at a given point, you can always follow those 5 steps, and that is going to be give you the answer that you want. So there's one last thing that I would like to point your attention towards, is that when you write the condition of equilibrium, is that the key thing to keep in mind is that the result that you get when you calculate the value of the unknown, the reaction support, will depend on how you draw them. So specifically the sign of the reaction forces from the support depends on how those forces are drawn, how you define them. So that's something to keep in mind, which means that first it is fine that in some cases, depending on how you draw them, you may end up with positive or negative unknown forces, but it doesn't mean that it changes anything regarding the physical reality of the system that you are considering. So, and the other thing to keep in mind is that it means that since the result that you get depends on how you draw them, you need to make sure that first you draw those forces and that you are consistent between how you draw them and the projection that you write in the condition of equilibrium. But again, keep in mind that the true reaction from a support, physically speaking, is always going to be pointing in one given direction, independently of how you draw it, because that's just the physical reality of if you push the material in one direction, the support is going to oppose this material. So let's just take an example to illustrate those different things. So let's consider that you have a given system like this, and you apply a given force on the left, and then this member is attached to a roller on the right. So let's consider this. And so I'm going to draw this system 2 times, and in one case, just for the sake of example, I'm going to say that I'm going to identify the unknown that is applied by the roller. So here you have the roller, so you have only one unknown, which is in this case is going to be horizontal force. So in this case, intuitively speaking, since you apply a force going towards the right, you would expect that the support is going to oppose the motion and create a force that is going to counterbalance F and go towards the left. So that's going to be the reaction of the support. But in certain cases, it's hard to have some intuition about whether the reaction will be pointing towards the left or pointing towards the right or pointing up, pointing down, or if it's going to be a moment that is clockwise or anti-clockwise. So at this point, it's perfectly fine if you don't have this intuition. You are free to draw the reaction of the support as pointing towards the other direction. There's nothing wrong with that. So we can say here that I define the reaction from the support as pointing towards the right. So then let's just solve the problem in the 2 cases, and let's make sure that independently of how we draw this reaction, that the physical reality of the fact that the support is going to oppose the force F is still going to remain the same. So let's write the condition of equilibrium. So when we write the condition of equilibrium, we will not get the same result here because we have not defined the force N in the same way. So its projection is going to be different. So let's write the fact that the sum of the projection of the forces along X is equal to 0. So in this case, so F has a positive projection along the X-axis, so it's plus F. Now in this case, I have drawn N as pointing towards the negative X, so its projection is negative N. And so the sum of F and N is equal to 0, which means that in this case, N is equal to F. So here we find that the reaction N is positive. It's equal to F, which means that if F is positive, so if F is indeed pointing towards the right, then n is going to be positive if it's pointing towards the left. So it means that in this case, I have drawn n, I have some intuition about where the reaction should be pointing towards. I have guessed that n should be pointing towards the left to oppose the motion of F, and indeed I find that if F is positive, then n is also positive, which means that my intuition about where this reaction support should be pointing towards was right. I find that the reaction force is indeed positive. It's equal to plus F, and it's pointing towards the left. So now let's write the condition of equilibrium in the second cases, which is exactly the same, but now I have defined the unknown as pointing towards the right, just for the sake of example, which is perfectly fine. So I'm writing the equation of equilibrium. So same thing, F is pointing towards the positive x, so this projection is positive. So now I have drawn n as pointing towards the right. So now n will have now a positive projection along the x-axis. So if I write its projection along the x-axis, then it's plus n, and it's equal to 0. So now it means that in this case, I find that n is equal to minus f. So now I find that the reaction n is negative, is equal to minus f. So if f is positive, if the force F is indeed pointing towards the right, then I find that the reaction n is negative. In this case, because you find that the reaction is negative, it means that your guess about whether this reaction should be pointing towards the left or the right was wrong. It means that and now you get a negative reaction, which means that you did not draw it in the actual direction that it should be going through. That being said, this result here is fine as long as you define n, as long as you draw and define n as going towards the right, and that then you find that this reaction is indeed negative, so that it should actually not going towards the right but going towards the left, then your result is self-consistent. So now the last question is, so in one case we find that n is equal to plus f, and the other case we find that n is equal to minus f. So does it mean that the system is behaving differently or not? So actually the system is still behaving always in the same way, right? Because if we now look not just at n, but we look at the projection of n along the x-axis. So now if we look at the true value of the projection n along the axis x to see whether the value of n that we have found and its projection along the x-axis, is it always the same independently of how we defined n? So we would assume that the physical reality of this problem is that if I put a force F pointing towards the right, then the reaction should be opposing this and should point towards the left. So if we look at the projection of n on the x-axis, this should not depend on how we defined the force n. So this is where we need to find that now the true result, the true physical reality, does not depend on how we defined the force n. So let's look at this. So if we want to calculate the projection of n along the x-axis, so I can write it nx. So what is the projection of n along the x-axis? So in this case, since I have drawn n as pointing towards the left, then it means that its projection along the x-axis is minus n. And in this case, since n is equal to plus f, it means that its projection is minus f. So in this case, we find that the projection of n along the x-axis is minus f, which means that indeed its projection along the x-axis is negative. This force is opposing f, which has a positive projection on the x-axis. Now let's do the same thing for let's calculate the projection of n on the x-axis for the second case. So now, because I have drawn n as pointing towards the right, now n has the projection of n along the x-axis is just n, because it's already pointing towards the same direction as the x-axis. And now, since n is also equal to minus f, again we find that the projection of n along the x-axis is always minus f. So just to summarize here, what we have seen is that the value of the unknown that you find depends on how you draw them, and it's perfectly fine to draw them one way or the other, as long as the result that you get at the end of the condition of equilibrium is consistent with the way you drew those reaction supports. But at the end, the physical reality always remains the same, right? Which means that the projection of the reaction that are actually occurring in the system, those projections still remain the same. The result that you get when you write the condition of equilibrium can have a minus sign or not, depending on how you define this reaction support. But the true projection in this case is always minus f, and this doesn't depend on how you draw this reaction support. So that's something to keep in mind. And something that we will come back, because that's a common mistake, is that if you consider a given force, the sign of this force depends on how you draw the force. So in this case, depending on whether you draw n as going towards the left or towards the right, the sign of this force can be either positive or negative. So the sign of the force depends on how you draw them, but the sign of the projection doesn't have to be the same as the sign of the force itself. So in this case, the projection of the force does not depend on how you draw them. The projection is always negative, and this does not depend on how you draw the force. So the sign of the force doesn't have to be the same as the sign of the projection of the force. So that's something that I would recommend you to think about to avoid future mistake, that the force that you are calculating doesn't have to be the same as the projection of this force. So that's something to keep in mind. Okay, so that's all that we are going to see in this chapter for the review of statics. So that's pretty much all you need to know of statics to solve problems for CE 108. So in the next chapter, we are going to start talking about calculating the stress acting within the material that is subjected to some external load. And the stress is what is going to allow us to calculate whether this material is likely to break or not. So that's what we're going to see in the next chapter.